Good morning, everyone. Welcome to this third day of the workshop on moduli and Hodge theory. Our first speaker is Sönke Rollenske, and will speak on stratifications in the moduli space of stable surfaces. Sönke?
Yeah, thank you very much. It's a pleasure to speak here, and it would be even more of a pleasure if here was actually in Miami. But yeah, my talk is, I hope for you, it's should be kind of relaxing because you have seen most of what I'm touched upon in the previous talks, and I'll try to fill fill this a little bit with life in a particular example and maybe add some flesh to it. So let's start. So it was implicit in several talks, but I'll quickly recall what I mean by moduli of stable surfaces. Then I'll propose several ways to look at stratifications of the moduli space or the compactified moduli space. And then I will discuss all these different ideas in a particular example, which is k squared equal to 2 and pg equal to 3. And I'll put special emphasis on the Hodge theory part, which is the topic of the conference. So let's recall every compact complex surface of general type has a unique canonical model, which I can recover via the canonical ring. If I fix invariance, then there's Gieseker's quasi-projective moduli space. And this sits inside the modular compactification, which parameterizes stable surfaces. This is due to Kolar, Shepard-Baron, and Alexier. So it's often called the KSBA compactification. So there's a warning. This compactification parameterizes stable surfaces, and there might be components which contain generically or which contain no smooth surface at all. So even, irreducible components or even connected components. So M bar is a bit bigger than the Gieseker moduli space. Okay, let me just recall for completeness what is a stable surface. A surface is called stable if it's S2 or Convex. It should have, okay, I didn't write it, but maybe it's implicit. I'm working over the complex numbers. It should have at most ordinary double points in codimension 1 and in total semi-log canonical singularities. And the canonical should be Q-Cartesian ample. Q-Cartesian is actually contained in the SLC condition, but I repeat it here for clarity. Okay, so if you do not know what SLC is, you should think about SLC as log canonical plus normal crossing. Okay, let's just look at some examples and pictures. So we know that on the canonical models, we already have canonical singularities, so ADE singularities. So here on the left, we have an E7 singularity. If I want to stay normal, I can add elliptic and cusp singularities. And here's a picture of a cusp singularity. We can see it looks slightly more complicated. And then if I go non-normal, then I have drawn for you a pinch point. You can see the normal crossing locus in codimension 1, and then the slightly worse point in codimension 2, namely this pinch point. And we have seen the pinch point already because it's one of these weird singularities. It's this nice example which you can give as an exercise for students. If you blow up the pinch point in the point, then you get another pinch point. So if you want to improve this one, you have to blow up the whole singular locus. And then there are worse singularities. This is a so-called degenerate cusp. You can still see the normal crossing divisor, normal crossing locus in codimension 1, and then in codimension 2 you get something worse. And if you look at it closely, you see this is actually the cone over a nodal cubic. So it is kind of, if you think of the simplest kinds of, if you think of simple elliptic singularities as being a cone over an elliptic curve, then the cone over a nodal cubic is not so much worse, except that it's non-normal and so. Okay, we have seen some local pictures. So here are some questions one might ask. What do stable surfaces look like? Maybe more globally than local pictures. Maybe one can ask which techniques and results that we have for smooth surfaces or say canonical models carry over to this stable case. And then originally we were interested in the moduli space, the Gieseker moduli space, so in say smooth surfaces of general type. So we should always ask, what can the compactification tell us about this moduli space, which we were originally interested in? But we can also go in the other direction and say, okay, assume we know all the surfaces in the moduli space. What can we say about the things that have to be added in the boundary? Just recall, the boundary doesn't need to be a divisor, can be any codimension, so it's slightly complicated, but what can we say about it? And I'm approaching this question more on a point-by-point level. So I'm not asking myself, okay, I'm not asking about the moduli space as a variety in itself, but I'm looking more at one surface at a time. What kind of surfaces are parameterized by M, and what kind of surfaces do I get which are parameterized by the boundary? Okay, this is, I mean, we know that Gieseker moduli space is already complicated or arbitrarily complicated. So this is a complicated problem. So let's try to get some structure into this moduli space by looking at some kind of stratifications. And just to fix ideas, let's think about what could we wish for. Yeah, and let me make an example where everything is nice. Here's the moduli space of stable curves of genus 2, and we stratify by, I think it's called topological type. So on the left-hand side, we have the smooth curve of genus 2, and then in the first degeneration, it acquires a node, and it can do so in two different ways. It can either be a separating node so that it splits in two elliptic curves, or a non-separating node so it is an elliptic curve with one node. Then it can acquire a second node. Again, it can be splitting or non-splitting. And so I have either two components or one component. And then it can be here on the right-hand side, we have the most degenerate curve, which is just these two rational curves glued in this way. Yeah, and in this stratification, we basically, I mean, this is just a baby case for all the moduli spaces of curves. We know that here we have two divisors. So the moduli spaces of dimension 3. Here I have two components of dimension 2. Here I have two curves, and then here I have a point. And I have also given you some arrows how they can degenerate to each other. So we have a very clear, very combinatorial picture, what happens at the boundary and how these pieces fit together. Okay, now let's look at some possible ideas what we could do in the moduli space of stable surfaces. The first one is not so much certification, but it is the problem that we have this big moduli space of stable surfaces, and we would like to single out the closure of the Gieseker moduli space, so, or it's sometimes called the main component. And this is what we really wanted when we started to think about compactified moduli spaces in the first place. But as far as I know, we don't really know how to do it. So it's not, we cannot get rid of all these extra components in a modular way. Okay, then there's one idea which we pursued for some time. So I look at the Cartier index. The canonical divisor is only Q Cartier. So I look at the smallest number when it becomes Cartier, and I or the surface is that way. So the Gieseker modular space sits inside M1. Oh, there's a bar missing here. Let me put a bar here. Sits inside M bar 1. The space of Gorenstein stable surfaces. And in principle, this is the index is bounded on each component. So Valerie Alexeyev knows much more about this than I do. And we could go on by induction, like doing index 1, index 2, and so on. And in the Gorenstein case, we have a lot more techniques. Basically, if intersection numbers are integers, then some things just tend to work out more nicely. And so you could think that you might want to go on by induction and just do one index at a time, but the problem is that there's no efficient bound. So I cannot, I mean, there are some bounds, but they are not practical to pursue this idea of just classifying all of them with index by index. Okay, there's a different idea. I just look at my surface, my stable surface, and I just look at the basket of singularities. So I just sort by the number and type of non-canonical singularities. This is very meaningful data, so it makes a lot of sense. But it's not so clear that I can, I mean, just give myself a bunch of singularities and then decide, does this kind of surface exist? Doesn't it exist? Also, I have these singularities in codimension 1. So two components might be glued along a curve, and then I have to remember maybe how this curve sits inside the component. So it's not just isolated points where I can just attach a number and be happy and think I know everything. So it's also not always very satisfying. Okay. At some point, I could just be fed up with all the singular stuff. And I just resolve everything and say, let's look at the minimum resolution. And clearly, we understand smooth surfaces much better than the singular ones. But unfortunately, this does not really work well in families. And when then on the resolution, I might have to keep, probably I forget most of it, but to get back my stable surface, I have to keep track of a lot of data on my surface, which kind of, what curves did I want to contract? How did I want to glue? And this kind of stuff. Yeah, so it's not always feasible. And then finally, there's this Hodge type, and it is a very natural invariant defined by a period map, but as we have been told, it's still work in progress, and it's sometimes not really easy to determine if I just give you the surface to determine the Hodge type and all this. I'll get back to this and explain this again, even if this has already been done by people who know more about it. But let's define this Hodge type. Yeah.
Is there how much of the Hodge data is recoverable from the stable surface on the boundary point?
I'll come back to that. Okay. So here's my stable. If I start with a stable surface, then I have Deline's polarized mixed Hodge structure on H2. And then I can look at the Hodge structure on H2, and it has weight, it has components of weight 2, weight 1, and weight 0. And I just, for this Hodge type, I just remember their dimensions. Yeah, so I just remember the R, which is the bits of weight 0, and the S, which is the dimension of the bit of weight 1 or 2S, and that's my Hodge type. So when I say this is, so actually, when you, yesterday Colleen talked about the limiting mixed Hodge structure, and I'm using Deline's mixed Hodge structure. So there's no degeneration here. There's no family. I have no limiting mixed Hodge structure. The only thing I know is by theorem of Steenbrink, and I think Radu also explained this, is that these numbers R and S. So if there is a degeneration and I get a limiting mixed Hodge structure, then these numbers R and S are the same for the limiting mixed Hodge structure and my Deline's mixed Hodge structure. And this is I think basically because SLC singularities are Dubois. So I think Radu yesterday and Matt pointed me to their paper on the Clement-Schmidt sequence. And I think you can recover a little bit more, but I'm very coarse. I just work with the numbers. So far, I just care about the R and the S and don't look for more like the extension data or something. Okay, let me, since Mark yesterday explained to us how to compute it, let's look at the modular space of curves again. So if I just use the Hodge type on H1 this time, my stratification gets a little bit coarser, and I have either the possibility that all the H1 has weight 1. This is the first bit, so the smooth ones and the ones where I get two elliptic curves put together, or where I have one bit of weight 1 and one of weight 0, or where it's purely of weight 0. And basically you can see, if you're not familiar with these computations, it's basically how much of the genus, the topological, how much of the genus is made up from the normalization and how much of the genus is made up from the combinatorics of the nodes. Yeah.
Is it the same as the Bailey-Borel stratum?
I think so, yes. Okay, so let's go back to surfaces. And the idea is that the Hodge type should give a stratification of at least of the smoothable part. But this was anyway the one we were interested in. And degenerations among these strata should obey so-called polarized relations. And I've written them down for pg equal to 3 because this is the example I'm going to consider. I start with a pure weight 2 Hodge structure, and then on the other side of the diagram, I have a pure weight 0 Hodge structure, and everything just keeps track of how I go from, how the individual dimensions can go down from weight 2 to weight 1 to weight 0. And I'm really using this as kind of a black box, or I mean, I just want to look at it and try to fill it with some life by putting in some surfaces here. So let's go to the example. We look at M bar 24, and this is for now I just start with the Gorenstein part, and yeah, Colleen pointed out that that I should have mentioned Matt Kerr and Greg Perstein for the possible degeneration. Sorry. So we look at this question from the beginning. If I know all the surfaces in the inside of the Gieseker modular space, if they are easy, what happens at the boundary? That's an example where I should have a chance to say what happens at the boundary. So this was worked out by my students, by my student Ben Anthes, and here's the theorem. So if X is a Gorenstein stable surface with K equal to 2 and Chi equal to 4, then the canonical map realizes X as a double cover branched over an octic. And in particular, since I can smooth out the octic, it is smoothable. So they're all smoothable. They're all in the closure of the main component. And conversely, if I have a plane octic, then I can take the double cover branched over B, and it's stable if and only if the pair P2 and 1/2 B is a log canonical pair. This is basically a baby case of a result by Alexeyev and Pardini on Galois covers. But the upshot is here, the only thing that we need to do is if you want to construct interesting surfaces, we have to construct interesting branch curves in. So basically we have reduced our problem to studying plane octics. Okay, this is, I didn't know how many graduate students would be here. So this is the educational part. I'm gonna go over it very quickly. So how do I work with such a, okay. So I want to look at explicitly how does this double cover of P2 behave. So I have a double cover over P2 X, and it's branched over a divisor in O of 8. So it's a plane octic. And my local model for a double cover is just, I have an equation F, which gives my divisor, and I look at the surface W squared minus F. So if my F is a plane curve in the affine plane, then my surface sits in 3 space. And, or in other words, I'm basically, W is a square root of F. So if you think birationally, I'm adjoining a square root of F to my function field. Okay, globally, so I need to realize this double cover equation globally. And since I'm working in projective space, I have this very nice possibility. I can just use weighted projective space. If I put the appropriate weights, then so if W has weight 4, then W square minus F is homogeneous of degree 8. And it defines the surface globally by the correct equation in weighted projective space. Okay. I can also do it in a line bundle. So I take the line bundle over 4, and then I take the total space of this line bundle, and if I pull back L to its total space, then I will have a tautological section in it. And then W square minus pi upper star of F will be a section of pi upper star of L squared. And again, I have globally written down my equation for the double cover. Is this really different from the thing we did before? Not really, because if you remove the singular point from weighted projective space, you get exactly this line bundle. So this geometric line bundle.
Why is the singular point an issue?
It's not an issue. It's just a different model. I mean, when you talk about double covers, it's often useful for me to jump between the different models for depending on what I want to do. So I wanted to present the different ways to think about them. So it's not an issue that it doesn't pass through the singular point, so it's not really an issue. You can also do this completely algebraically. Clearly, you just X is the spec. It's a finite morphism. It's the spec of the push forward of the structure sheaf, and the structure sheaf is O of B2 plus L inverse W with the multiplication W squared is equal to F. So again, I have realized this time globally algebraically my equation W squared is equal to F. Yeah, and if you don't mod out this equation from this sheaf of algebras, then you get exactly the line bundle. So this is just different ways to look at the same thing. Okay, so let's look at some double covers and let's see what kind of singularities of the branch curve. So clearly by the Jacobi criterion, the double cover is smooth if and only if the branch curve is smooth. So let's look at singularities of the branch curve to get what kind of singularities they induce on the surface. So here you have the canonical singularities, and just for completeness, recall that by the slide before, if I want to get the surface singularity, I have to add t squared. No, it was called W. So W squared minus this one in front of it, and this gives me the A1 surface singularity. So so that's the way you do it. So here the canonical singularities, and these we know well. Then we might get simple elliptic singularities where the exceptional divisor is a smooth elliptic curve. You can get something which is an ordinary quadruple point, or this one is called a 3-3 point, because you have a triple point and an infinitesimally near triple point. And then when you take the double cover, you get elliptic singularities, simple elliptic singularities, but the elliptic curves have different squares. And then when you degenerate these curves, when you impose extra tangency conditions, then you will get, as an exceptional divisor in the minimal resolution, a cycle of rational curves. Since we are Gorenstein, we are looking at Gorenstein surfaces. We don't need, you could also look at a lot of quotient singularities on these surfaces, but we are Gorenstein, so no quotient singularities of these. So, okay, so these are the kinds of singularities we are looking at in the branch curve. So if I have these surfaces, so I should, before I look at it, I should clarify from the surface, how do I get the Hodge type? And the idea is that there's a theorem due to Pardini, I think, that if you have a proper contraction of a curve to a point, then there's a Mayer-Torres exact sequence of mixed Hodge structures of this form. usually you think when you say Maya-Vietoris that you have decomposed something so into 2 bits, but one of the bits that that you decompose it into is basically the point, and the point has no reduced cohomology, so it just disappears from the exact sequence. Yeah. So now I think as X my stable surface and Y the minimal resolution. Say X is normal, so I just contract a bunch of curves from Y to X. And what do I see? If the singularity is rational, then my exceptional divisor will be rational. So it will not have any H1. So it does not change the Hodge type. Yeah, I get a 0 here. And this 0 tells me that all of H2 of X is of weight 2, because it all comes from Y. Okay. So, since every non-Gorenstein log canonical surface singularity is rational, these singularities do not change the Hodge type. It does not mean that the Hodge type could not be very interesting on surfaces of higher index, that you could mess about with, I mean, if you could have a quotient singularity somewhere and then some Gorenstein singularities somewhere else that do interesting stuff to the Hodge type, but as a start, we can just leave out the quotient singularities because they don't affect these numbers R and S. Okay. What is with simple elliptic singularities? They have an H1 of an elliptic curve. So they will have something of pure weight H1 in the red bit of the exact sequence. And then this could give something in X of weight 1, but it could also be killed by H1 of Y. Yeah, so there is some issue here which you might have to check. If it actually shows up in the hot structure of X, or if it just gets killed by H1 of Y. But once you have a cusp singularity, then as we have seen in the genus 2 curve case, the H1 of the exceptional locus, which is now a cycle of rational curves, will actually be of weight 0, because all the genus 1, that is arithmetic genus 1, comes from the fact that it's a cycle. So from the configuration of nodes. And thus it will have weight 0. Weight 0 cannot, I assumed Y to be smooth, so weight 0 cannot be killed from Y. And so it all moves to H2 of X. So it will introduce something of weight 0. Okay, so our idea is I have to impose some elliptic singularities, simple elliptic singularities to get bits of weight 1, and I want to impose some cusps to get bits of weight 0. And then you can prove the following lemma, and this is really proved by picture. Every Hodge type and possible degeneration of Hodge types is realized in this moduli space. This is good news because a priori, I mean, the Hodge type should see something, right? And it should be meaningful for our modular space. So it's good news. And let's do this with pictures. Okay. This surface, the first one, has, you see, I have taken 4 conics in the plane. 4 conics is an octic. And they have a lot of double points. Yeah. So double points give A1 singularities, and A1 singularities are rational, so they don't contribute to the Hodge type. So A1 singularities are fine. I could take a smooth octic here as a starting point, but it's easier to see that all these degenerations exist if I already start with 4 conics. Okay. I want to drop one of the, I mean, PG is equal to 3. I want to drop one of the dimensions into weight 1, so I impose 1 elliptic singularity. It's here. right? Here you can see the ordinary quadruple point, and the ordinary quadruple point we know gives us an elliptic singularity of degree 2. And you can also see it in the picture on the right. It becomes more complicated. Okay, and now it's just, I mean, the main work here is to find the nicest equations for the nicest pictures, really, right? So what do we want to do? We want to degenerate this further to get a cusp. Yeah, so we need to impose a further tangency, and that's what we do. Yeah, here again, this one gives me the cusp. Okay, and now I'll just slowly go through the pictures. I impose 2 quadruple points and a bunch of A1s. This gives me, so I should check this, that it's really happening, but it drops 2 dimensions to weight 1. Then I add another tangency in one of the points. It drops 1 of the weight 1s down to weight 0. And I add another tangency. It drops both of them down to weight 0. I have 3 quadruple points giving me 3 simple elliptic singularities, thus dropping the dimension, I mean, all the PG down to weight 1, 1 more tangency, 2 more tangencies, 3 more tangencies. Yeah, so this surface has 3 cusps. So far it looks very nice. The Hodge type really appears and distinguishes some surfaces in our partially compactified moduli space. I'm just looking at the Gorenstein part. So let's now look at it from the other side. What doesn't it see? Okay, we have discussed when we looked at the exact sequence that maybe at some point an elliptic singularity might not be picked up by X because it gets eaten by the minimum resolution. And indeed, if all the Hodge type, I mean, if all the PGs down to weight 1, then you can have either 3 elliptic singularities. We have these 3 quadruple points here, or 4 singularities. That you can have 4 ordinary quadruple points on an octet is really easy. Through 4 points, you have a pencil of conics, so you just pick 4 general conics in the pencil. So you get 4 quadruple points, which means 4 elliptic singularities. So they cannot all have an impact on the Hodge structure because PG is only 3. So only, I mean, they're kind of all equal in a sense. The minimum resolution in this case is a ruled surface over an elliptic curve, and the elliptic singularities are kind of 3 different sections. So they are all equal in this map to
Will the
H2 of
limiting
X.
structure in the family see the difference?
Sorry, say again?
Will the limiting Hodge structure of Mark and Collins see the difference?
I mean, I assume that Mark can give you some way to, so as in the example of the genus 2 curves, you can certainly distinguish the say a smooth genus 2 curve and the union of 2 elliptic curves in a point via the Hodge structure. Even without any limiting stuff, you can distinguish them, but not by the numbers. I'm just playing a numbers game. I don't know if some extension data can distinguish these 2 cases. The minimum resolution is different. So in that way, maybe you find some different extension data somewhere there, but I'm not sure.
I think the extension data in this case will at least generically distinguish the where the points are.
Okay. So I'm just looking what the numbers can see, and not at the finer structure in the Hodge structure. Okay, let's look at one interesting stratum in detail. So this 0,2 stratum, it means that of my 3 dimensions in PG, 1 dimension has remained of weight 2 and 2 dimensions have become weight 1. So you would think, okay, I get this if I impose 2 elliptic singularities. That's what we expect, and that's also what happens. But you can impose these singularities in different ways. So there are 2 different types of elliptic singularities that you can have, namely degree 1 and degree 2, depending on the square of the exceptional divisor, exceptional curve. And so here in the first column, you have this N11 and N22. Okay, I should read this completely. So Ben proved that in this stratum, there are 4 irreducible subsets of normal surfaces and some non-normal ones. So the first one, N11 and N22, they differ by, the first one has 2 elliptic singularities of degree 1, the second one 2 elliptic of degree 2. So they are somehow distinguished by this. And then the second column, we have N12 prime and double prime. So it has 1 elliptic of degree 1 and 1 elliptic of degree 2. And they are different in the sense that one, the minimum resolution is a K3 surface or a properly elliptic surface with PG equal to 1. So even for the same kinds of elliptic singularities, you still get 2 irreducible families of surfaces. Let's look at this. So we have N12 prime and N12 double prime. And the difference between these 2 families is that here, this was this 3,3 point. And as you can see, this 3,3 point has a distinguished tangent direction. And in fact, it's easy to see that the tangent line to this 3,3 point has to be part of the branch data. But the difference between the 2 cases is that in this case, the quadruple point does not lie on this distinguished tangent. And in the other case, this one is the 3,3 point. And maybe I take the blue one. This is the quadruple point. Here's our quadruple point. And in the second case, the quadruple point is contained in this distinguished line in the plane. So you get these nice pictures of surfaces. And if you're bored, you can try to find the K3 in the N12 prime and the elliptic pencil on the N12 double prime. Again, Radu alluded to this. So these surfaces, they are double covers. So there should be, so the involution, if you lift the involution to the resolution, then you should think that the K3 surface that occurs should also be a double cover and of a rational surface. So you can take a blackboard and then draw a nice big diagram to understand what kind of special K3 surface occurs and what kind of special configuration of branch curves for the K3 do I need to have to get my my branching data here. of this kind to get a surface in n12 prime. I think I know the dimension of n12 prime, or I don't know it, but I have it written somewhere. I can look it up. Okay, so this is what can happen in this stratum. Oh, let's look at the non-normal ones just to have the pictures. We have this non-normal surface, which is very easy to get. You take a general sextic and then add 2 times the general line to the branch data. The general sextic, the normalization, will give you the K3 surface, and then twice the line will give you the non-normal locus, which has, which is generically normal crossing, but then has these pinch points where the line intersects the sextic. So it has 6 pinch points, and the rest is normal crossing. Here in the first picture, you can see the 6 pinch points. In the second picture, you just see 2 of them. Just to make the connection, to keep everything concrete, just think we want to be in the 0-2 part. So there should be a 2-dimensional or rather a 4-dimensional Hodge structure of weight 1 around somewhere, which is the weight 1 piece that is in the Hodge structure of X. And what is it? Well, if you look at the pre-image of the line, of this double line, which we have in X, you can see it on the right, then the pre-image in the K3 surface is a genus 2 curve. And the Hodge structure you see is exactly the Hodge structure of the genus 2 curve in the K3 surface. So it's very it's very concrete. Okay, I've talked about some Gorenstein degenerations. I've illustrated some Hodge-theoretic stratification and other kinds of stratification ideas with these degenerations. We should say something about non-Gorenstein degenerations, and we haven't explored this case fully yet. I think Marco and Julie will talk about this I-surface case a bit more in detail, but the one idea is very simple. So let me just show you one example. I can degenerate this P2 and 1/2 deoctic, and then take double covers to get degenerations of X. You can also make this precise in some functorial way, but then one concrete example is I can write down this degeneration Y. Downstairs, it degenerates the projective plane to a P114, which is the cone over the rational normal curve of degree 4. And so the central fiber downstairs has 2 1/4-1/1 singularities, has 1 1/4-1/1 singularities. And if I take a branch cover, which is branched away from this singularity on the double cover, I get 2 of them. And then, yeah, so you get these 2. I mean, this is an example where the index is 2, and then you can get all kinds of other examples, probably by degenerating this, or I could now try to smooth one of the 1/4-1/1 points, and but this goes beyond what we can do now. Okay, let me recap. So all these kinds of stratification ideas can help you to organize the surfaces you find in the boundary. One particularly interesting one is this Hodge type. And on the other hand, our knowledge of degenerations is still very limited, even in simple cases. I mean, what simpler case could you imagine where your general surface is the double cover of P2 branched over the smallest possible curve such that I get something of general type. Right? This is really the easiest analog of a genus 2 curve in higher dimension. And if you ask people in the working on modular spaces of curves about the genus 2 case, then they will not take you seriously, right? In this case, we really, I mean, we can describe the Gorenstein locus. This was done by Ben, and but beyond this Gorenstein locus, it's really open. So when I write the problem is surfaces of large Cartier index, then maybe I mean 2 or 3. Even 2 or 3 are possibly difficult. So thank you very much and stay safe in these troubled times.
Okay, thank you, Sönke. That was a marvelous talk, and we have time for questions or comments.
Maybe, so if somebody else has a question, maybe they should go first, but I do have a question. So it seems that all your, I mean, Colleen and Mark and your talk seem to suggest that stable surfaces maybe are not the final answer. Maybe you want to have stable surfaces together with the data of an extension of the Hodge structure, of the limiting Hodge structure, the extension data of the limiting Hodge structure. Is there a chance of such a moduli space where, you know, you parameterize pairs of the geometric pieces, a stable surface, the additional piece is shift-theoretic, it's an extension of the Deligne structure to a limiting Hodge structure, to a maybe pre-limiting. You don't know that it's a limit of something, but it behaves like one. Is there a possibility of such a moduli space? So that automatically Colleen's extension theorem will be encoded in it.
I honestly have no idea.
Can I just briefly comment? So what, I mean, what would that be? Would be some sort of the moduli space together with like a simultaneous semi-stable reduction over the moduli space. So basically the basic example even is when you have a stable surface with a simple elliptic singularity, that surface will not remember kind of the Del Pezzo tail. So I think this was already in the Mark Stoke or that. So if you do a semi-stable reduction, you'll blow up the simple elliptic, you'll get an elliptic curve, but in the family, you'll get also Del Pezzo surface, and that is encoded in the limit mixed Hodge structure, but not in the limit mixed Hodge structure. So basically, that's what I would expect to hold in general. So the limit Hodge structure also remembers the smoothing direction that you choose. So in some sense, you are blowing up the locus. I mean, this simple elliptic locus has high codimension, and you transform it into a divisor or something like this. So that would be nice if it can be put together in a moduli space. But yeah.
Thank you.
Sönke, I had a quick question. I just wondered if you managed to construct any other examples with the Weil singularities using just degenerations of P2.
I mean, I didn't try in this case. And we did something in this iSurface case where you are a double cover branch over the quadric cone. And then it was kind of more in the other direction that we found some example, which was in this case, singular and weakless surface glued to a singular K3. And then then in order to construct the smoothing of this, to see if this is actually in the boundary or not, you construct, I mean, you reconstruct the degeneration of the quadric cone, which then falls into, I mean, a very basic, the easiest case is where the quadric cone becomes two planes in P3. And then you take a double cover of this, you get two case-free surfaces. So that's something which we saw very early. And then the others were more the other way around, that you had a surface from somewhere and then afterwards you reconstruct the degeneration of the base of the double cover because you need it to smooth it out. One could indeed look at the other direction to see which degenerations are of P2 would maybe give you something interesting.
Yeah, I was just going to mention, you know, in my thesis, I described degenerations of P2, and there was like in the case where the degree of the curve is not divisible by 3, there's a sort of algorithm to figure out which of them actually occur in this space where you look at P2 together with a curve and you insist that basically, you know, in your case, it would be P2 plus an optic, and you'd want it to be a half plus epsilon log canonical. So instead of your coefficient being a half, it would be a half plus epsilon. Probably it's the same as what you're trying to do in this case.
Is it a half plus epsilon, or is it? I remember that it was even smaller. So because you wanted K.
Oh, I'm sorry. You're right. Yeah, you're right. Yeah.
So
that's
Ben,
right. I'm sorry. Yeah, 3/8 plus epsilon.
Ben did some comparison and gave some examples of things that curves that would appear in your moduli space and still be in P2 and would not be still not be log canonical. Yeah. So your space is a bit smaller, I guess, than the one we would need to look for.
Yeah, sorry.
So you would have to go from whatever it is to 1/2 and have like a bunch of transformations.
You know, there's some long list of, well, there's an infinite list of the generations of P2, and then there's some kind of way to check which would actually appear just by, you know, bounding the singularities. Once you have this degree on the curve.
Yeah, so that's...
Yeah, and I also thought maybe I should mention, you know, you mentioned the quadric as well. So there is this work of, I think it was Chang-Ho Han at Harvard. He's now in Georgia, I think, and Anand Diopaka. They were looking at a quadric with a curve, and they were trying to construct degenerations of a similar nature. So there was some work in that direction as well for the quadric. But it's not terribly complete at the moment.
I'm not aware of that. So if you have a link for that, I would be glad.
Sure.
Yeah.
Is what Paul's saying related to Kristen de Fleming's thesis?
Possibly. But kind of. So there's this, I mean, I don't understand these small coefficients really well, but there's this, like you have the coefficient where it's actually trivial, and then on the other side it becomes Fano and the pair, and then so the case Paul is looking at, it's when it's as small as possible or nearly as small as possible, and our coefficient is kind of far away from that. I mean, so there's some way to go there from these moduli spaces that they have, and the idea somehow the smaller I can make the coefficient, the worse the singularities can get. So so in our moduli space, so where let's say where his curve stays in P2, in the stable moduli space, or the moduli space where the coefficient is 1/2, his curve is no longer allowed. So the surface already has to split off some component to make room for the curve singularity. So it will tend to have more components and be more complicated, the surface itself, than because the curve, I cannot hide the complexity in the curve singularity. I have to like make room for it in the surface.
I mean, presumably one can set up some sort of variational approach, kind of. I mean, Paul's compactification is pretty close to the GAT, and so he blows up some stuff, but still pretty close to that. And then, as the coefficients gets bigger, you move away, but presumably it can be done. It can be done in a continuous way, so that, I don't know, if you have a very good algorithm and stuff like that, you might be able to relate the two and track. I mean, in some sense, this is the idea of what Asher, Liu, and De Fleming did, maybe a bit in the opposite direction, kind of towards the Fano case, but still kind of in the same.
So there is a preprint that has been hanging around for over a year because there are 4 authors and they have not released it. So it's Baileri, Asher, Baileri, Inchiostro, and Potok-Folvi. And I think it's time to pressure them to actually release it, about wall crossings precisely in this situation.
Mm-hmm.
Yeah.
Okay, if there are no further questions or comments, again, thank you, Sönke, for a very nice talk, and we will reconvene in 25 minutes at 10:30 for the second talk this morning.